Okay, this time I got stuff recording for those who can't make it. Let me move it to the side. Bum, bum, bum. I'll wait maybe 2 more minutes for anyone else who wants to join, and then I'll get started. Yeah, I should really ping, to be fair. Hey guys. We're going to be looking at differentiation. This is a transition from year 11 to 12. However, it is very useful for those in GCSE as well. Yeah, or GCSE for the maths. I think this information is still very helpful for even if you're going to year 11. And practice makes perfect for maths, so I don't think it hurts. If you are going to take A-level maths, I really recommend having just some sort of prior knowledge before you guys do anything, because it's a big jump from GCSE to A-level, and most schools, if they don't do further maths as well, it's hard. It's really hard. But yeah, I think it looks good. I think I'm gonna get started. I am recording. Let me just check. Yes. Okay. I'm going to cover the proof of differentiation again really quickly for those who weren't here last time. So, let's get started. I'm going to just draw a curve graph real quick. Something like that. Okay. Now, to work out a gradient of any line, for those who weren't here, do you guys remember how to do that? Yeah, dy by dx. But careful, we don't call it dy by dx because it represents really differentiation itself. For gradient between two different points, we call it change in y over change in x. Okay, the d means something special, and I'll get to that in a second. Okay, and that's our gradient function. Perfect, doner kebab. That's a nice name. Okay, if I call this first point x, let's call this point x here. And I don't know what this graph is, let's just call it f of x. Okay, this point here is going to become f of x. Happy with that? Is everyone happy with how functions work? So let's say we have a function of... Alright, perfect. Okay, so if this point was x plus h, if we went h along, this point would become x plus h. and this area here, this y coordinate here, will become not f of x, but f of x plus h. Okay, now we can apply our rules of gradient, working that out, and we can say that our change in y is really the difference here over the difference in the x-axis. And I'm just going to write that down here. Alright, so our difference in the x-axis is h. Our difference in the y-axis, I've written that down as just a normal subtraction. Even if we subtract in the bottom, this is just basically what's going on. Here it just cancels out, and we're just left with h. Okay, now as h approaches nothing, as it gets smaller and smaller, our gradient becomes smaller as well, but it approaches the singular point of x. Furious Fist, it's more for GCSE further maths, but this information, I think it really just helps you build a foundation. So if you feel you don't really need it, and you're not going to take A-level maths in further education, this session, up to you. You can stay, but I think it can really increase your knowledge in general. And maths is more of a skill-based lesson rather than memorize. So up to you if you want to stay. Okay, so as I was saying, this is our gradient function for this line. As h approaches, it gets smaller and smaller. I'm just going to draw another tangent here. Tangent line, not tangent yet. Okay, our line slowly becomes just at that point. When h is just nothing, we end up with a tangent at that singular point of x. Okay, and we write that as h approaches 0, and then we just put limit on top. Limit, and then this is basically our formula for working out any gradient at a singular point. So let's say I have x squared, y equals x squared. Okay, let's say I have y equals x squared. I'm going to call it, in fact, f of x equals x squared. What's going on here? What's going on here? That's weird. Strange. I thought it stopped working. Oh, that's irritating. That's irritating. Oh, there we go. It started working again. Okay, f of x equals x squared. Okay, and this graph looks something like this. Okay. Now let's say we have a question, and GCSE students, you will see this quite frequently. It might be like, okay, what's the formula of a gradient? What's the formula of a gradient at a single normal point? So at a point, and then we have a normal of it. Okay, we have a point there, and it wants to work out the equation of that line. Okay, it wants to work out that equation of that line. We can use differentiation to quickly work it out in a snap. Okay, so first step. Okay, do we know what facts do we know between a normal and a tangent? What facts do we know? There's something relevant between a normal and a tangent. Yes, perfect. Okay, they are perpendicular, so there's always a 90-degree angle between them. Okay, so what we can do first, in this hypothetical situation, I'm going to get to some practice questions in a bit. Okay, we can work out the tangent gradient here, at this point. Okay, we don't have to do any, for example, we draw a tangent. For example, if they give you a graph, okay, if they give you a graph in the exam and they're like, okay, draw a tangent, and then give an equation of the tangent, or what's the gradient, okay, you can draw it, but the examiners don't actually measure your tangent. They look at the answer. There's always an answer below it saying, give me the gradient, and they have a range. Okay, we can be very, very accurate with that range if we have a formula. Let's say we have x squared plus 3. We have x squared plus 3. We can use our formula here. We call this the first principles. Okay, we can put it in this formula, and whatever our x point is, let's say this is 5. We could put 5 in, and then we'll get the gradient. We'll get the gradient at that point. I'll be very, very accurate. In fact, not even accurate, 100%. There's a 0% error in this, and I'll get to that why in a moment. Let me just rub this out. Okay. Now let's scroll up here and let's look at this formula. Now, what does this limit mean? As h approaches 0, okay, this means as this h here, if we put in a number, it slowly becomes close to 0. Now, it can never ever become 0. If we put a 0 in the denominator, we end up with undefined. Similarly, this is why when we have a reciprocal graph, 1 over x, we get two different answers. From the positive side, this is slowly approaching plus infinity. However, from the negative side, it is approaching negative infinity. They never do actually touch this y-axis line. Let me just. They never actually touch. However, they approach it. Okay, and that's why we get two different answers in this case. With differentiation, however, you are able to manipulate it using algebraic skills, and we can get a single answer. Okay, I'm going to go through one gradient function with you guys. You can have a go at it if you like as well. X cubed. I'm going to differentiate this using the first principles. These are very important when going into year 13, so it's very important to memorize this formula, especially when you're doing trigonometric differentiation. I'm not going to go into that today. Okay, let's start. Let's say this is f of x. Okay, you guys can continue with me. Okay, and I'm going to substitute. So f of x plus h will be that. Okay, now I'm going to expand this all out. I'm going to use binomial distribution. Further mathematicians, they will know about this. I'm not going to go through that today. Maybe another future lesson. But you can use any expanding method, you know, FOIL, grid method. I personally use the grid method, it's very useful. Okay, I'm going to use a binomial distribution on this. Two, 1, 0. Okay, and this becomes plus x cubed. Okay, and then we minus our x cubed from here, our f of x, and that becomes all over h. Okay, now remember, this h can never actually become 0, but the idea of it as it approaches 0, we end up with an answer. I'm going to go to a graph that I developed earlier last week, if you guys were here for that lesson. I went through this in a bit more detail. However, I've posted a link in the chat where you can just experiment around with differentiation. If you mess around with the a value, you can clearly see how the line moves along a singular point. And that's the tangent, and that's what we're going to work out. We're going to work out a function. And this here, you can see this is relevant to our first principles. Okay, next I'm going to simplify this. Okay, no worries. If I recommend you look at functions. Okay, I am recording this, so if you look at functions and then watch that video afterwards, I'll probably post it in the chat, maths channel, and then you can possibly hop on in the next lesson as well. Okay, so this cancels out. Okay, next I'm going to just factorize this top part here with a common of h. Okay, this h cancels out, and we're just left with h squared plus 3xh plus 3x squared. Okay, now we need to remember, theoretically we should actually really write the limit every single time, especially in exam conditions, but it's not too important as long as you know what you're doing. Now as h approaches 0, h squared, that's going to be 0 squared. 3x times 0 is just 0 plus 3x squared. We end up with just 3x squared. Okay. Now, as you can see, when we continuously repeat this pattern, for those who were in the last lesson, we noticed that there was a pattern, and we didn't actually have to use a formula every single time. So our original formula was x cubed. Now dy by dx. I can't remember who said that. No. You're only required to use it to work out. It's more for proof rather than what's it called? Rather than you to use it. Because, for example, when you constantly do it, you learn the pattern. So you can just straight away say dy by dx. This is just the writing thing. What's the word? This is a way to tell us that it's been differentiated. D meaning very small value, and that's why we have the h approaches 0. So we can just say dy by dx equals 3x squared. We don't have to go through all of that. However, you can come across questions saying prove that x cubed, 3x squared is a differentiation of x cubed using the first principles. When it says the first principles, it's just talking about the formula, and you're expected to remember that. In second year A level, you'll come across this thing called small angular approximations. It's just sine theta equals, when theta is really small, is theta. Tan theta is approximately theta, and cos theta I believe is 1 minus theta squared over 2, approximately, when these values are very small. However, this is not necessary for your first year. This is used for your this is used to prove what the differentiation of, for example, sine theta. Okay, we use this to work out the differentiation for that. So don't worry about that too much right now. I'm not going to go through that. Okay, and this will be our answer here. I'm going to go through some practice questions. This time we actually have more time than last time. I'm going to put some practice questions here. If there's any questions, please do let me know. Oh, most of the guys left. Okay, no problem. I'll go through some harder stuff then, because I don't have to do all that. Let's try these. One moment. Here we go. Here we go. Can everyone see that okay? Okay, have a go at that. You are permitted to use a calculator. That's completely fine. A-level maths, you're literally allowed to use a calculator for everything. There's no non-calculator exams. Okay, I'll go through it all in 5 minutes. If everyone's done. Looks nice. Okay. Pascal's triangle, yes, there is a way of remembering it. I've just done up to 5 so many times. I just know up to the 5. After that, I can't really know, but there is. What you can do, you can start with a 1, and then you can do 1 2 1. Okay. After that, these two numbers, they add together. So always on the outside, you always have 1s, and so 1 plus 2 is 3. 2 plus 1 is 3, and then we just have a 1 on the outside. And then we keep repeating that pattern. 1 on the outside, 1 plus 3 is 4, 6, 4, 1. And you keep on repeating that, and then you have your, well, Pascal's triangle. Like that. There's a bit more of a rule to it. I think you do cover in year 1. I'll go over in a proper lesson with that. Okay, I'll go through the first one real quick. I'm going to change this to 3 x to the 1/2 using our index laws. Okay, dy by dx, that becomes 3 times 1/2, which is 3/2, x 1/2 minus 1/2, 1/2 minus 1 is minus 1/2. I'm just going to rearrange that to a nicer looking thing. I believe that is right. Yes. Okay. Next, I put in the number into x, and I get first one's going to be 3/4. B is going to be 1/2, or 3/6. I forgot to mention for the recording, the rule is nx to the n minus 1. Okay, so we multiply the indice by the number behind, or if it's just a 1x, and then we minus 1 from the index. Okay, you can, if you apply it to loads of different equations, you will see this pattern, and eventually it will speed up your process. Let's do C. Divided by 2 is 1. C is going to be 3, I believe. That's going to be 3/4. 6/4. 2 divided by 6/4 equals 2 times by 4/6. 8/6. And the last one's going to be 8/6. If there's any corrections, or if you feel that you're right, please do let me know. I might have made a mistake. Okay. I assume everyone's okay with that. Okay. Let's see this. I assume everyone's okay with the first one. I'm going to go through extension 1 in 1 minute, 30 seconds. If you do need more time, please do let me know. Okay, first I'm going to rearrange this so it's just y. Okay, so it just ends up as y equals 2y squared minus x cubed equals 0. I'm going to add x cubed on both sides. I'm going to divide by 2, and then I'm going to square root. Okay, now when we square root an entire fraction, we can actually, in fact, we can leave it like this. But we want to differentiate this. Let's check. Yeah, we need to differentiate it. So when we have a square root of an entire fraction, we can write two square roots like this, like that. But remember, square root is actually to the power of 1/2. We can write it like that. This is the same thing as, well, x to the 3/2 over 2 to the 1/2. Now I'm going to rearrange this a little bit more. Times by 1 over, like that. And then I'm going to use our index laws again. Like that. Okay, and this becomes our, well, something to differentiate. We can't multiply them together. In fact, we can't simplify them because they don't have the same bases. So we have to just differentiate like this. How do we differentiate this? This becomes, let's use our rules. This becomes x 3/2. Okay, we put our 3/2 in the back, and then we're going to subtract. And then this is being multiplied, so it would become, what would it become? This one's slightly trickier one. 10 by minus 1/2. Give me a moment. Which question is that? Two. Okay. This becomes, well, 1 over 2 times by 3/2. Differentiate. Okay, we're going to differentiate that. Apologies for the mute. 3/2, we're going to differentiate. That becomes 3/2√2. Let me just write that again. In fact, yeah, we can simplify that because it's being multiplied. Yep, so that becomes 1/2. Yes. Okay, is everyone okay with that so far? No worries, Emma. Is everyone keeping up with that so far? I think I may have gone a bit too fast. Okay, I'm gonna rewind then. We can multiply them together, or we can keep them separate. It doesn't really matter. I'm gonna just change it back into a root like this. I think it's just nicer to work with. Doesn't really matter. This becomes, well, like that. 3/2. This is the same thing as like that. Now I'm going to differentiate. 3/2 times by 1/√2. That becomes 3/2√2, and then I'm going to subtract 1 from our index, like that. And this is the same thing as this times by root of x, so this becomes that. And that'll be our answer for that one. That one's a bit more tricky, but I hope everyone's okay with that. You can write this in multiple ways. Oops. 3/2. Like that. Or like that maybe. These are all acceptable. Is everyone okay with that? Does that make sense? It's not specifically asking us for a gradient, but it's asking for a function, the gradient function. So we don't have to put in a value for x. Okay. Inverted, you were going to type something. I'll take that as you are okay. Alright. Let's go through. Yeah, perfect. I'm going to give you some time for extension 2 if you haven't got to it. Let's do that. I did want to get through second derivatives in this lesson as well, but I don't know if we'll have time. We do have 20 minutes. And maybe we'll go through something else as well. Ooh. Okay, I'll start on the first one. Find the gradient of the curve y equals x squared minus 5x plus 10 at the points A, B, where the curve meets the line y equals 4. Okay. Okay, this will look like, well, we have a 10 there. This will become x minus 5x. Left side is on the right side. Equals minus 10 minus 5/2. I think it'll be floating actually. Maybe something like that. Might be wrong. Let's just say it looks like that. Okay, we have y equals 4 here, and we want to work out the gradients of the curve. Let's say this is A and this is B. We have two different points, and I want to work out the gradients at the 2 points. Okay, so that's y equals 4. I want to know the x coordinates. So first step, what I'm going to do is I'm going to substitute 4 into here. So that becomes 4 equals x squared minus 5x plus 10. Subtract 4 from both sides. Factorize. And then solve for x. Okay, now I have two different values for where we have our intersection, 2 and 3, and these are our x coordinates. Next, we can differentiate dy by dx. Now I'm going to apply the nx n minus 1 rule that we had from before to each individual value. X squared, that becomes 2x, minus 5x becomes just minus 5, and plus 10 disappears, and we're just left with nothing on that. So that's our differentiation function for this graph, question 5. Okay, next I'm going to substitute 2 and 3. That becomes 4 minus 5, which is minus 1 at A. Yep, we can see it's negative. Okay, and second one, 2 times 3 is 6, 6 minus 5 is positive 1. And we can see it's going up. And those will be our 2 answers. Have a go at the next one and let me know if there's any questions. Let's move it to the side. There we go. Okay. Alright. Let's start with this one. Question 6. I'm going to go through it slowly, so if you guys haven't finished yet, you can still get to finish. Y equals x plus 3 and y equals 2x squared. Find the gradients of the curve 2x squared at the point C and D where the curve meets the line y equals x plus 3. Let's try drawing it first. 2x squared will be like a stretched version of an x squared graph. Maybe something like that. And x plus 3 will look like this. Okay, that's our x plus 3 graph. Now we have 2 points, C and D. Okay, let's stretch this out. Some more space. There we go. We have some more space now. Okay. To work those intersection points out, we can equal them to each other. X plus 3 equals 2x squared. I'm going to equal one side to 0. Next, I'm going to look for a way to factorize. It might not always be factorizable, but let's have a go. 2 times minus 3. That gives us minus 6. Now 2 numbers in minus 6 that add to make minus 1 here. That's going to be 3, minus 3 and positive 2. Okay, now this is a method that I've learnt. It's helped me so much, and it's honestly speeded up my factorizing. I'm going to take this 2x even, and then I'm going to just copy the values down that I got on this side. Okay, now this is not the finished factorization because 2x times 2x is 4x squared. I'm going to look for one bracket or even both. Most of the times is one. Look for one bracket to try and simplify down if there are a common number between them. Okay, this right bracket here does, and I can make this into x plus 1. And this becomes 2x minus 3 times by x plus 1. And we can expand this out again, and this should equal to our original quadratic. I'm just going to use a grid method to work this out. And this does equal our original quadratic. Okay, so here our x solution will be 3 over 2 and minus 1. Next, I want to find out the tangent at that singular point. There we go. And how will we do that? Done with the quadratics. I saw this method. I learned this method from Hegarty Maths originally, back in year 10. Very, very useful. Saved me so much time, honestly. Okay, I'm going to differentiate. Our original function was 2x squared. We need to be careful. Do not differentiate this second equation that we got, because that's our solutions to the intersection points. Okay, we need to differentiate using this original equation, 2x squared. Okay, 2x squared is equal to, when we differentiate, that becomes just 4x. Next, we just plug in our values. Minus 1 times 4 is minus 4. And for D, 3 over 2 times by 4 is 12 over 2, which is 6. And that's our two gradients. Now you will come across this question, or rather you use this method to quickly just work out whether something intersects or not. Okay, so if I said, let's say we have x squared plus 5, and then let's say I have x minus 12. Okay, let's say we have these two different graphs. I want to know whether they intersect or not, but I have no idea how to quickly draw them in the middle of the exam. Okay, it might be something more complex. This is quite easy to draw actually, but I'm not going to draw them straight away yet. I want to know whether they intersect or not. Is there any intersection points? Is there a point to even equaling them together? Okay. What we can do is, first we have to combine them the same way that we have done above, to try and look for an intersection point, but we're not going to solve for it. Okay, so I'm just going to equal them together. Let's say there was an intersection point. In this case there isn't, and you might have a question: prove that these two graphs don't have an intersection point, or prove they have one intersection point, prove that they have two intersection points. Okay, and this thing is called the discriminant. If you do further math GCSE, you might have heard of it. Okay, x squared plus 5 equals x minus 12. I'm just going to bring everything to the left hand side. Minus x, 5 minus 12 is minus 7, I believe, equals 0. Now, this thing is called the discriminant. You might have seen this before. This is from our famous quadratic formula. Okay, just this part here is actually normally in a square root. Okay. However, this part here, because it's in a square root, whenever it's less than 0, this is where we have a not real number. Okay, an undefined value, if you put into a calculator, let's say we have the square root of minus 36. We can't do that because it's a negative number. When you square anything, let's say we square minus 7, we end up with 49. We square positive 7, we end up with positive 49. We can't square something and end up with a negative number, except one thing. This is called I. And this is an imaginary number, the square root of minus 1. You might have seen this somewhere, and they don't actually discuss it in A-level maths. I don't know why. It's only further maths actually. But I think it's good knowledge to know why something happens. Because you can't square root it, mathematicians back in the day, they decided to make this imaginary number. And today it solves many problems. Many problems. But when you square this, I squared, we end up with negative 1. Okay. You don't have to worry about that too much right now. But if your square root, the stuff inside the square root is less than 0, we're going to have a non-real number, an imaginary number. So they do not intersect. On the imaginary graph plane, on the imaginary plane they do, but you don't have to worry about that. Okay, if it equals 0, we have exactly one intersection point, so it's normally a tangent. Okay, if it's bigger than 0, we have 2 points of intersection. Now we can apply this to, for example, just normal quadratic. Let's say we have x squared minus 5x plus 6. We can apply this and adjust to this, and this will have 2 intersection points with the x-axis because it has 2 roots, real roots. Let's go back to our original equation and let's see whether it does have any intersection points. I believe it shouldn't, but let's check. So a in this case is 1, b in this case is minus 1, and c is minus 7. Note, the discriminant does not actually have the square root when you're working this out, so make sure you don't have like a square root of whatever. Okay, keep it without the square root, that's the discriminant. So a is 1, b is minus 1, so that's going to be minus 1 squared is 1, minus 4 times by 1 times by minus 7. That brings us 1 minus 4 times by minus 7, and that is 1 plus 28. Oh, apparently it does have 2 points. We did 29. Okay, 29 is bigger than 0. And let's check. Let's check whether it does have any intersection points. Did I go wrong somewhere? 4 times 7. I went wrong somewhere. 4 times 7. Let's check this again. 5 minus 12 is minus... this is why. This is supposed to be plus 12. No, not minus 12. It's alright, but I went wrong as well. Okay, so I went wrong up here. I'm supposed to subtract x and then add 12. So this should be minus x plus 17. There we go. Now let's try it again. B squared, that's going to be minus 1, so that's just 1. Minus 4 times by a, which is just 1. I'm not going to write that down. Times by 17. 17 times by 4 is 68. 1 minus 68 is minus 67. And we can see that's smaller than 0. And if we go back to the graph, they do not have an intersection point. Honestly, I do wanted mics to be open, but for some reason they've disabled it. I'll probably let some moderators know. What do you mean by advanced A-level topics? Specifically. Because this is probably not that advanced, but I think it's opening my own server. Would anyone join? Don't know. Because loads of people joined at first, the session. Tricky over that. Okay. Fair enough. You happy with discriminants? Because we still have some people who haven't done differentiation, so it's important for them to know as well. But yeah, I was planning to go over to second derivatives. You don't cover that in further maths. Planning to go into basic integration. No, don't worry. It's more or less 9 o'clock anyways. But let's see what else I had planned for the lesson. Second derivative. Do you? I think yes, you do. Yeah, you do. Yeah, we do. But very briefly. I'm going to quickly go over that. Second derivatives. Yes. d2y of dx squared. I'm going to go over this briefly just for recording as well. I think recording is about an hour now. Yep, 57 minutes. Okay, when we have our point here, let's say we have 3x squared from our original x cubed. Okay, when we ever put whatever gradient we get, like that. And that's our x cubed graph, kind of. In fact, I'm not gonna do that. That was better. Okay, so we have three different. In fact, we have two stationary points, and then we have 1 point of inflection on a cubic graph. The second derivative. So basically, we got let's say this is it's not actually x cubed, but I'm just gonna say it's x cubed. Let's go back to like 3x squared. We differentiate our dy by dx. That becomes 6x. Now, whatever our value is here, let's say this is minus 3. Okay, let's say this is minus 3. If we put this minus 3 into our d2y of dx squared, we can see whether it's a maximum point, a local maximum point, or a local minimum point. Obviously, in this graph here, there is no maximum point because it just goes on to infinity, and there is no negative point because it goes over to negative infinity. Why I'm saying it's local maximum point and local negative point is a turning point over when it's stationary. So in this specific area. Okay. Inflection point is when it doesn't have a minimum point or a maximum point, where it's basically turning. It's literally the point of turn, if that makes sense. Okay, so here, how we would prove that this is the maximum point, we can see that the gradient is going down. So if we put this number into this function here, it won't be right in this case because this is for a different graph. If we put this number into here, we would end up with a negative value, and that's how we would say yes, it's the maximum point. However, for this point here, let's say this is 5. If we put it into our second derivative, we will end up with a positive value because it's going upwards. It's going up. So we would say yes, that's the minimum value. And to prove that these are the minimum values and the maximum values, we have to first equal our first derivative to work our stationary points out. Otherwise, we don't know that they are the maximum or the minimum. We can obviously pick a point up here, and it will end up going positive because obviously it's increasing upwards. But we can't say that's the maximum point if we don't know that it's stationary. Our gradient being 0 at that specific point. If that makes sense. What else was there? There was drawing. N minus 1 times by n minus 1 times by nx n minus 2. So let's say if we consider this to be n. Okay, I see what you're trying to do. Let's call this u, and then I'm just going to change it. Instead of n, I'm going to call it u x u minus 1. Okay, so if this is u, this becomes, well, no, that's wrong. No, that's wrong. N minus 1, because not always necessarily n minus 1. But you see, yes, it will be. Yeah, you're right. Yeah, you're right. Yeah, so it would be n minus 1 times by nx to the n minus 2. Yes, that is maths. That is the fun of maths. But it gets more interesting than that. This is not the limit yet. But yeah, I don't recommend learning it like this. I recommend just learning the first one and then differentiating with the rule that you already know. Don't overcomplicate things if you don't need to. If you feel that you need to learn that better, it's completely fine. What else was there? I think we covered drawing derivatives last lesson, but I'm going to quickly check that again. Let's say we have a cubic graph like that again. Okay, and I want to draw the derivative of it. Okay, first of all, it's going up here. It's increasing in our value. Okay, at this point here, it's 0. Our gradient is 0. So here, we're gonna have a 0 function. Okay, our gradient is slowly increasing, and it's slowing down. Okay, so it's going to be above the x-axis here. It's increasing, but it's slowing down. It's coming towards 0. Okay, here it's going into it's still positive, but it's going into negative. Okay, after the stationary point, so it's going into negative, and here it goes to 0. Negative, and comes back to 0. The gradient 0, and after that, positive. Oh look, we've drawn a quadratic graph. We've drawn something that looks like a quadratic graph from our cubic graph. If this was, let's say, x cubed plus, I'm just going to say it's a stretched out version. Let's say it's that. No. Okay, let's say that's our gradient there, function there, and this might be, well, that. It's probably not the right differentiation, but you can see. Actually, it might be minus 3. Yeah, maybe something like that. But you can see when we draw a derivative, we can clearly see why it turns out to be a quadratic graph, why it happens. And we can differentiate this again, and we'll end up with a straight line this time. Okay, this is slowly coming down, and here it approaches 0 at this point. This is our 0 point here. So here is our 0. Okay, it's slowly negative. So it's going to be here until the 0. So negative until there, and after that is all positive. Straight line. Okay. And from here, that's our second derivative drawn out. They don't specifically ask for you to draw it out, but I think it's cool to know. What else? I don't want to go over integration yet. In fact, have a go at differentiating backwards. I'm going to give you a function. Let's say x cubed. Something when you differentiate it, it becomes into x cubed. What is that something? Think of this as an introduction to integration. When you differentiate something, it turns into x cubed. What is that something? Let's see how much I actually got through. What's left? Yeah, doing normal. Doing more practice on that. X cubed. Okay, let's try x cubed. If our original value was x cubed, okay, if our original value was x cubed, we try to differentiate that. It's going to be 3 minus 2, so it's going to have a 2 in the front, okay, 3 in the back, like that. Nice, inverted, perfect. Okay, so we're going to have a 4. The 4 goes with 3, okay. We need something, 4 times something, to become into 1. Okay, so that's going to be 1/4. 1/4 times 4 is just 1, and then we subtract 1 from the index, and that becomes 3. Okay. Now there's also a rule for this. You'll end up finding a pattern. I want to let you guys try to figure that out. I'm going to give you another one. Plus 5. Okay. I want you to integrate this function. That's basically what you did here. Nice. MX, are you okay with that? Okay, so it's going to be 1/3 x cubed. Okay, the 3 multiplies here, and we're going to subtract 2. That's perfect. This is going to become an x squared, but we need 2 divided by 2, which is just 1. And then we end up with 5x. But remember, it's not just going to be 5x. For example, if we differentiate this function here, this becomes 2x plus 2. But you can see that this 5 disappears, because it doesn't really matter what the y-intercept is, because we're working out the gradient function. We're not bothered about what the y-intercept is. So here, it could be anything. So we say plus c. Always plus c. If this was plus 7 there, it wouldn't really change anything at all, because the plus c, well, here it would, but in the derivative afterwards, it would not. Okay, so when we're integrating without a limit, and I'll get to that in a second, when we're integrating without a limit, we have to put a plus c afterwards, because we don't know what that plus c is. However, if we do have a limit, let's say, let's see how this graph looks like actually. Okay. Alright, it looks something like that. Okay. Alright, that's our x squared plus 2x plus 7. Let's say I want to work out the area of what between these 2 points. Like that. Let's say this is minus 2 and this is 4. Okay, I will just put a minus 2 here and a 4 up there. Okay, and that way we basically have a formula that we can apply this is our integrating formula, and we basically use that. But the plus c doesn't really matter, so we ignore that. Okay, when we're integrating. But if you have an indefinite limit, we put plus c. Okay, and yes, inverted. That's our rule. N plus 1. It should be x. It should be like this, like that. I believe. Is it? Yeah. So whatever the number is before it, we divide it by our index. Okay, not times, but divide. That's our little introduction to differentiation. I want to do more normal questions, but I think you guys are actually quite confident with that. So if you guys really want me to, I can do another lesson next. What guy are you guys happy with the lessons? If you guys do want more, and what day would suit best? Because I don't know if Monday is quite annoying to work with. If Sunday's better, then I can do that. Alright, perfect then. What days does it suit you guys? Weekends or? I know some people at work. I work myself, so that's why I can only do this time. But I can do Sunday quite more or less any time. Okay. Alright, no worries then. Perfect. Yeah. Alright, that's perfect. Let's see what the next part was gonna be next time. Sketching gradient function, look at that. Ooh, differentiation, but in terms of not graphs, but something else. Okay, that's interesting. Yes. Okay. Alright, we'll do that next time, and then move on to some integration. Alright, cool. Am I following spec? Kind of. I've got a textbook. So it's Edexcel textbook. But it has it's mainly questions rather than lessons, if that makes sense. No, I can't be bothered with English. It's just no. I cannot be bothered with English anymore. The moment I know, when I went out of school in the last day, I was so happy with no more English. I despise it. The amount of work I've put into even try to get a good grade, especially because I'm doing STEM. Yes. I'm not bothered if he's PM or not. Just know English. That's my concern. Exactly. I finished this year.